So this is a continuation of the solutions for our techniques final, and we were in these triangular questions, so we're going to start over here. So use the given values to determine the missing values for all possible triangles. Here we're given side lengths only, so I'm going to label them 3, 5, and 7. And we need to figure out what our angles are. So law of cosines does a nice job of telling us what our angles are using a little bit of inverses. We just have to decide which one, or which ones we want to start with. Like we mentioned on the problem above, because this angle is opposite of the largest side, the 7, this angle might be obtuse. We don't know. It might be obtuse, or it could be acute. We don't know. Which is fine with law of cosines. Law of cosines gives us one answer between 0 and pi, and the other answer is in quadrants 3 and 4, which can't live in triangles. So law of cosines is fine to find angles that might be acute or obtuse, but law of sines is more ambiguous. So when we're finding that particular angle, we want to make sure we're either using the law of cosines to find it, or that we have the other two angles and we're just subtracting from 180. So what that kind of, essentially what it means is we either want that largest angle to be the first one we find or the last one we find. And I think it's a good habit just to make it the last one you find. Just that way, no matter what the problem is, like the problem above, just make the possible obtuse one. Always find that by subtracting from the 180 for the full triangle, and you'll never have to worry about it, except in that angle side case where ambiguity is part of the problem. So I'm going to follow that trend and find that angle opposite the 7 last, and here that angle is going to be angle C. So the 3 is opposite angle A, the 5 is opposite angle B. Okay, so we're going to find that the C last. You could find it first if you wanted to. Technically, you could find it second using law of sines. You would just have to then deal with that ambiguity, and that can be an unnecessary pain. So, just by strategy, don't do it. So we can really find either of the other two first. I'm going to go ahead and find A first, just, alphabetical, why not? So, law of cosines, tells us that A squared equals B squared plus C squared minus 2BC times the cosine of the angle opposite A. So why don't I label that capital A just to be clear. And in this case, we know all the side lengths, and we're just going to use this to solve for angle A. I did mention in the last video, or the video on law of cosines, that we can always solve this formula for cosine A and use that version. It does end up being another formula we'd have to have on our sheets or memorize, so I tend to say just stick with this. But you can either solve for the cosine first or plug your numbers in, whichever you want. I'm going to go ahead and just start plugging in some of our numbers here. So 3 squared equals 5 squared plus 7 squared minus 2 times 5 times 7 times the cosine of our angle A. So 9 equals 25 plus 49 minus 70 times the cosine of A. So 9 equals, 74 minus 70 cosine A. Again, be careful about subtracting those. I know I mention that every time, but it's such a danger. So if we want to continue solving for a, we got to subtract that 74 off, and we'll get negative 65 equals negative 70. Cosine a, divide the negative 70, and we get 65 70ths. The signs cancel, equals cosine a, and I would be tempted to reduce that to 13 14ths equals cosine a by dividing out the common 5. This is less than 1, so that tells us it can actually happen. That's nice. So angle A, we're going to find whatever the cosine inverse of that 13 14ths is. And the nice thing, because it's the law of cosines, we can go ahead and use the principal answer and be pretty safe. So cosine inverse, oops, I want the inverse. Cosine inverse of 13 14ths is going to be 21.8. So 21.8 degrees. And of course, or anything coterminal, but we're not going to care about the coterminals. Or we get the answer, 338.2 degrees, and anything coterminal to it, but those can't happen in our triangles either. You don't have to write that, but like the plus or minus, we want to be in the habit of remembering that we're ignoring them on purpose. So angle A, 21.8. This was a pretty small side length at 3, so that being a fairly small angle seems reasonable to me. Now, here's the important part. The next one we're going to find using law of sines. We could use law of cosines again to do it, but law of cosines is a lot of work. Law of sines is a lot faster, but needs to be strategic. So we're going to use law of sines, but we're going to use it to find angle B, because again, we know angle B has to be acute because it's not opposite the largest side. There can only be one obtuse angle, so the only option is that obtuse angle to be opposite the 7. The middle angle has to be acute, so we know B is acute, so we won't have to worry about the ambiguity from law of sines. So we know that the sine of angle B in ratio to its length has to match the sine of angle A, the 21.8 degrees we just found, in ratio to side A, 3. So the sine of B is equal to 5 times the sine of 21.8 degrees over 3, and a little sine inverse will give us that answer. So sine inverse of 5 times the sine of 21.8 divided by 3, 38.2. Okay, so 38.2 degrees. And of course, or and everything coterminal, but we ignore those. And the 141.8 degree angle in quadrant 2, which would normally be possible because 148 degrees can fit in a triangle just fine, but it can't be a middle angle. That would mean this angle C would have to be also obtuse, would have to also be obtuse because it has to be larger than angle B because it's opposite a longer side, and you can't have two obtuse angles in a triangle. So we get to throw that one out because of our strategy. So 38.2. degrees. Now C, maybe it's obtuse, maybe it's not. Clearly with these small angles it has to be obtuse. But the nice thing is, because we're now going to be finding it by the fact that the angles have to add up to 180 degrees, we will get that obtuse angle naturally without having to worry about the ambiguity inherent to law of sines. So that's going to be what, 59? No, it's going to be 60. Oh, that's fun. So that's a 6. 60 degrees. So it's going to be a nice 120 degrees. Quite obtuse. So again, up to our rounding, none of those are exact. So 120 degrees, and we have all of our angles. So a little bit of strategy, always really helpful for those. Okay, a little bit of vectors. We haven't had a lot of time with vectors. Luckily, we're not doing anything too terribly complicated with vectors, other than getting used to the notation and the symbology and the vocabulary, which is plenty. I'm going to work this over here. Okay, so given these two vectors, or actually these three vectors, find the difference between W and, or between V and W. So the vector V is I hat minus 2 J hat, and W is 2 I hat, that should have a hat, I don't know why it has a dash, plus 3, that should be J hat. That's my fault. There's a little bit of typing issues on those. Yeah, that should be an I hat, a J hat. So if we want to subtract those, we're going to be taking I hat minus 2 J hat and subtracting 2 I hat plus 3 J hat. So 1 minus 2 is negative 1 in the I. We don't need the 1 there, but I'm going to put it there to be handy. And then negative 2 minus 3 is negative 5 in the J. So V minus W is negative 1 if you want to write it, or just negative I hat minus 5 J hat. Okay, 2V is going to be 2 times our vector V, so 2 times our I hat minus 2 J hat. So that's going to just be 2 I hat minus 4 J hat. We're just distributing that 2 very naturally. Again, that's why this notation is not. Ooh, there was a negative in front of that. So that's a negative 2. So that's a negative 2. So that's going to be negative 2 I hat plus 4 J hat. So, ooh, careful about that negative. Negative 2 I hat plus 4 J hat. Now this one's got more pieces in it, which might seem like it's going to make it more complicated, but as long as we're comfortable with the notation, it's really just tracking that notation. 2 times V, and V is again I hat minus 2 J hat, plus 3 times W. W should be 2 I hat plus 3 J hat. Sorry about that typo up here. And then minus U, and U is 3J, which we can think of as 0 I hat plus 3 J hat if you want to. So if ever one of them is missing, it's still there. It's just it's just a 0. So if you want to think about it that way, you don't have to write it that way, but if you want to think about it that way, it's perfectly fine. So 2I minus 4J plus 6I plus 9J minus 3J minus 0 I's, again, if you want them. And then we're going to collect like terms. So we end up with 8 I hat, and then negative 4, negative 3, and positive 9 is going to be a positive 2 left behind, J hat. So we're going to have 8 I hat plus 2 J hat. Cool. So, as I said on our video about vectors, the mechanics aren't really anything different than the kind of algebraic manipulation you've been doing for a long time. It's just getting used to the notation, the symbology, the vocabulary, which is not an easy thing. Those are usually some of our most difficult things. But it's nice to have at least one of those things be nice. Find a unit vector in the same direction as W. Well, W, that full vector, again the 2i plus 3j, that vector has its own magnitude and is heading in a particular direction. All vectors are like that. Vectors have magnitude and direction. So if we want to point in the same direction as W, we have to keep its direction, but make its magnitude 1 unit to make it a unit vector. And we're going to do that, make a unit vector in W's direction. Again, that's what the hat symbolizes. By taking our vector, and dividing out its own magnitude to bring its size down to 1. So we need the magnitude of W, so it's going to be the square root of 2 squared plus, well, 3 squared, which will be 9. So 4 plus 9's square root, or the square root of 13. So we're going to take our vector W, the 2i plus 3j, and divide by the square root of 13 to make it a unit vector in W's direction. And again, that's what the hat symbolizes. So we're going to divide that into both pieces. So 2 over the square root of 13 in the I, and we do want to break this up into components. So we don't want to leave it in this form. This is a vector with an operation being performed on it, where this is a vector. We should still rationalize because we are, polite people. So 2 square root of 13 over 13 in the I plus 3 square root of 13 over 13 in the j. But that's going to be our unit vector in W's direction. So essentially, the vector going in W's direction, where we've stripped off the meaningful magnitude and just left a direction in a unit vector. Okay, so vectors, I think this is our last one, isn't it? Nice. So our vector V has an initial point and a terminal point as given. It is always good, really, to draw a nice little diagram. So it has an initial point at 3, -5. So 3, -5 doesn't have to be a great diagram. 3, -5. Like, we could label our axes and put a scale in if we wanted to, but it's just to give us a visual reference for our own work. But a terminal point at 2, -1, so that's 2, -1, so somewhere around there. 2, -1. So that's our terminal point, so we'll be headed in this direction. And if we wanted to, we could, imagine we're going to be writing it in standard position, so we're going to be pretending it's over here. So the nice thing about drawing even a quick little diagram is it gives us an idea of the kind of angles and kind of magnitude we should be looking for. But anyway, write it in component form. Well, component form, get my pen back. For that vector V, well, it's going to go the difference in the x values, x2 minus x1 in the I direction, and the difference in the y components in the I direction. So that's how much vertical or horizontal displacement in the x and vertical displacement in the y is going to give us our vector. Do be careful about your order here. It is always end minus beginning, so it'll be 2 minus 3 in the I, and then -1 minus the -5 in the j. So it's going to give us a -1 in the I and a +4 in the j when we have our -1 plus 5. And that should make sense. It is going that way 1 and this way 4, so a -1 and a +4 make reasonable sense in the orientation of our diagram. Again, it's a nice reason to draw a diagram so you can kind of make sure your answers make sense. So that's your vector v in component form. You could also have written it in position vector form if you wanted to express it in position vector form. If you were asked to do that, that would be fine as well. The process is the same. Now, trigonometric form, if you recall, trigonometric form has the magnitude of the vector multiplied by the cosine of the angle in standard position that the vector is at in the I, plus the sine of the direction of the vector in standard position in the j. So it still has, the ij pieces. If you distribute the magnitude, you get component form, but we have the pieces are separated, and we're using trig in the direction. So if we want to express that, we need to figure out what the magnitude of this vector v is, and we have to figure out what angle in standard position this thing is at. But the nice thing is we know how to find both of those things. The magnitude is the square root of the sum of the squares of the components, so -1 squared plus the 4 squared is going to be the square root of 1 plus 16, or the square root of 17, so that's our magnitude. And we can find the angle by noting that the tangent of our angle is equal to our b over a, or our y over x, if you want to think about it that way. So the tangent of our angle has to be, what, -4 over 1, or just -4. Go ahead and write it. So the tangent of theta equals -4. And that will allow us to find our possible angles, and we can then interpret which angle we need. So might as well do this in degrees. We're not told one way or the other, so we could technically do it in degrees or radians, but let's do it in degrees. So the tan inverse of -4 is going to give us a -76. So -76 degrees. But of course, we also know we get any half rotation. Normally it would be pi k if we were in radians, but 180 degrees k because we're in degrees. So the -76 degrees is the angle within our restriction, because we know tangent only exists between -pi over 2 or pi over 2, so between -90 degrees and +90 degrees. But we don't want that angle. That angle is the angle opposite what we need. We need this other angle. So we need one of those coterminals, or one of those opposite lengths. So we need this one. So we're going to take that principal and add that 180 degrees to get, what, 104 degree angle. Yeah, so this angle, after we added the 180 degrees, is our 104 degrees. So that is something to always be careful of. That's why, remember on your notes, I didn't like that your formula said theta equals the tan inverse of b over a. That's not always true. It's not always the principal solution. Sometimes it's the other solution. So it's better to think of it as the general solution to tangent of theta being b over a. But either way, we get our trigonometric form, the magnitude, square root of 17, times the cosine of 104 degrees in the I, plus the sine of 104 degrees in the j. So that's our trigonometric form. And it's a fun thing to test. if you did distribute that 17 and get the square root of 17 times the cosine of 104 degrees in the I plus square root of 17 times the sine of 104 degrees in the J, 17 times the cosine of 104 degrees should equal, approximately, because we're approximating here, but should equal negative 1. And the square root of 17 times the sine of 104 degrees should equal about 4. The only reason it's an approximation is because this tan inverse, that 76 is an approximate value. There were decimals on that. But it's fun to make sure and check. Did we end up with the same thing? Yeah, this is about negative 1 and that's about 4. So we did end up where we were supposed to end up. Okay. So that's your second part for your techniques final. I'll make a video for the application final shortly, so that should be up as well. And if you have any questions on any of those, send me a message, let me know.